Rohit Kumar Singh, the TA for this course, Nuclear and Particle Physics, and this is the 12th live session for the 12th week of this course. So this is the last week, but there will be an extra session next Saturday, just to remind. And so this week we had lectures on uh, weak interaction and how how we can write the Lagrangian for electroweak uh, theory, and what are the symmetries that we have in this theory. So I will try to recap some of the concepts, and starting from the QED, quantum electrodynamics, and then I'll go through some examples so that you will be able to solve this week's assignment. Okay, so let's start. So so last week you must have seen this you must have seen this Lagrangian uh, so this is the Lagrangian for Dirac theory, and its equation of motion gives you the Dirac equation. So you solve the Euler-Lagrange equation and you get the Dirac equation out of it. But but if you try to have some kind of local gauge transformation, for example, if you take psi to exponential of I alpha, alpha is a function of x, psi, and the psi bar prime equal to minus I alpha x psi prime. So this is what we call local gauge, sorry, yeah, local gauge transformation. So if you do this in the Lagrangian, the new Lagrangian, which is L prime, it becomes, so I is psi bar prime, gamma is same, and then psi prime minus m psi prime psi, psi bar prime psi prime. Okay, and if you put these two equations, for psi prime you put this, and for psi bar prime you put this, what you will get is, so you will get a term. So I'm not doing this explicitly because it has been done in the lectures. I'm just recapping things. You will get these three terms, okay? And this, if you see, it is same as the uh, Lagrangian defined for the Dirac theory, right? But you have an extra term here. So, so then we see that this Lagrangian is not invariant under local gauge transformation. Okay, and to have it invariant, we'll have to redefine uh, the momentum operator, basically the I del mu. So we redefine it to be uh, this. So why this? Uh, so if you see now, uh, you can define something like capital D mu equal to del mu minus I e a mu. Okay, and now a mu prime you can define as so like this. Okay, and then you can write the Lagrangian above like this. So now you replace the differential del mu by d mu and keep others same, and now this will be invariant under uh, the local gauge transformation that we have defined above. Okay, and its equation of motion you can write, you can solve the Euler-Lagrange equation and you will get its equation of motion to be this plus this term. So you see, this is the Dirac equation, right? And then you have another term which we call the interaction term. Okay, and so this equation says that if you want to have a local gauge transformation included, you have to include an interaction term which is the interaction between the the electron with the surrounding electromagnetic field represented by the a mu. Okay, so this is how you interpret this, and then then if there is an electromagnetic field, you must have to add the electromagnetic Lagrangian, which is uh, the Lagrangian for the free photon f mu nu f mu nu, right? And with this you get the full Lagrangian like this. So bar del mu psi, this is the Dirac Lagrangian. Then you have the interaction term and this is the Lagrangian for free photon. And if you define a current, so this is the electron current, then you can write it more concisely as this. Uh, 1 by 4 F mu nu minus J mu A mu. And this whole Lagrangian is the Lagrangian for quantum electrodynamics. So here this is the term for free electron, and this is the term for electron interacting with the electromagnetic field, and this is the term for the electromagnetic field itself, that is the photon. Okay, so and this whole Lagrangian is for quantum electrodynamics. And solving it will give you this equation of motion, which is the equation of motion for an electron in an electromagnetic field, interacting with an electromagnetic field. Plus there will be the Maxwell equation added here. Okay, so yeah, this was the brief recap. So do you have any question here till now? So these are done in more detail in the lectures. I'm just going over it once. So let me know if you have any doubt. And so this local gauge transformation, this comes from this is called the U1 symmetry, because these e to the power I alpha x, this belongs to a group called unitary group, and of one dimension 1, and this symmetry of the Lagrangian is called the UN symmetry. Now similarly, the weak interaction has a different kind of symmetry, which is called SU2L. So SU2 we have seen before, it is the group of special unitary matrix of dimension 2. Okay, and L here is for L here denotes that only the left-handed particles participate in the weak interaction. So for example, only the left-handed leptons like electron and muon and taus, all those are left-handed. So EL, muL, tauL, and then you have neutrinos corresponding to them. They only participate in the weak interaction. Okay. So this has been observed experimentally. Okay. and there are no right-handed neutrinos yet found. So this is a kind of a mystery. uh, if we find one right-handed neutrino, this whole theory breaks, the whole theory of standard model breaks. And I mean, many experiments in around the world are trying to find a right-handed neutrino, but so far they have not been successful. Okay. And similarly, only the left-handed quarks like UL, CL, I mean, this is the up quark, the charm quark, top quark, and then you have dawn quark, strange quark, and bottom quark. Only the left-handed, they also participate in the weak interaction. Okay. And this SU2L symmetry, uh, it manifests itself as a isospin value. So you make doublets of, for example, you can make doublets of neutrino and electron, and uh, this should be invariant under SU2L symmetry. Okay, so this is a doublet under SU2L. Okay, so what does it mean is you can define isospin. So in case of strong interaction, you saw that we can define an isospin for neutron and proton with proton plus half and neutron minus half, and uh, we saw that many things get simplified if you define if you define isospin like that. And similarly, in here in weak interaction also we can define a kind of isospin. So for example, uh, we can define uh, so for this doublet, for neutrino and an electron, we can define a isospin of half with I3 plus minus half. So third component of isospin, plus minus half. So plus half for the neutrino, left-handed neutrino, and plus and minus half for the electron. Okay, and similarly you can have other doublets like up quark, down quark, all left-handed, because as we see, only the left-handed particles participate in the weak interaction. Top, bottom. So all these are doublet under the SU2L symmetry. And the right-handed particles are singlet, so they are not invariant under this symmetry. And then so not going into detail, I just quickly want to mention the electroweak theory. So electroweak theory is a unification of electromagnetic theory and the weak theory, like the weak interaction. And here the gauge symmetry is given by SU2L. This is for the weak, and then the U1, which we saw is for the electromagnetic theory, and this Y here denotes the hypercharge. So you can so we define a quantity called hypercharge, and this is the equation. This is called the Gell-Mann-Nishijima formula, and here with this, so why we have defined something like this? So you see the doublets that we have defined, that we saw, for example, the neutrino and the electron. So if you calculate the hypercharge for this, so the charge of neutrino is 0, right? And I3 is plus half, and so if you calculate Y, you get -1. And similarly, the charge of electron is 0, and the third component of isospin is -half, and again charge of electron is -1, and if you calculate hypercharge, you get -1. So you see the hypercharge for all the elements of the doublets are same. Okay, similarly you can calculate the hypercharge for all the quarks, and you will see the hypercharge for UL and DL will be same. Similarly, CL and SL will be same. So all the doublets will have the same hypercharge. So that's why this is a convenient quantity. Whereas if you calculate the hypercharge for right-handed particles, you will get you will see that so the Y for example, right-handed electron will not be equal to the Y for the right-handed right-handed neutrino doesn't exist. So let's say if you calculate Y for the up right-handed up quark, this will be not same as the Y for the down quark, but for left-handed the opposite case is true. And so only the left-handed particles participate in the electroweak theory, electroweak interaction. And here the transformation, the local gauge transformation is given something like this. So just to mention, so this is the local gauge transformation for electroweak interaction, and it falls under this symmetry of SU2L cross UN. Here this I are polymatrices basically, and alpha we already know this is the constant from the gauge transformation of electromagnetic theory, and Y is the hypercharge. So yeah, these things have been done in more detail in the lecture, so please go through it once if you have not yet. And then later we see that this cannot be an exact symmetry. So for example, uh, you cannot have mass terms in the Lagrangian if you consider this symmetry. So this symmetry has to break in order to have, massive particles. And so breaking and then breaking this symmetry explicitly by adding the mass terms to Lagrangian, this leads to various problems, and the way out is the spontaneous symmetry breaking, which leads to the uh, you know prediction of Higgs boson. Uh, so yeah, this is a very nice way of uh, reaching to the Higgs boson through theoretical implications. So if you have not gone through the lectures, I suggest you go through it. Professor Paulos has very I mean, in a very simplified manner, he has explained these things. So it will be very good if you can go through it and understand everything. So what I will do is I will quickly go through some problems, examples, so that it will help you in the assignment. So do you have anything ask in these concepts? Okay, thank you. Then let's go to the problems. Okay, so the first problem is so consider a Dirac fermionic field psi and a complex scalar field phi and photon given by a mu with the covariant derivative. So this we just saw, right? So we define the d mu like this in order to have a invariant Lagrangian under the gauge transformation. Then the question is, which of the following terms are invariant under the gauge transformation? So this is the gauge transformation that we just saw. So so let's do this. So psi goes to, so I'm not writing lambda as a function of x. We can understand that it is a function of x. If psi goes to exponential I lambda psi, then psi prime will go to minus e to the power I lambda psi prime. Okay, and similarly, if phi transforms like this, phi star will transform like this. Now this psi is a 1 cross 4 matrix, right? This is the fermionic spinor 1 by 4 matrix, and this phi is a complex scalar field of 2 dimension, right? So that's why we have here bar and here star. And yeah, a mu is transforms like this. So if you check in the first equation, so del d mu phi star d mu phi. Okay, so whole prime, so this will go to, so d mu star phi star prime d mu prime phi prime, and we can put so for d mu star prime, you can write del mu star minus I e a mu. So because it's the conjugate, we'll have to replace the I by minus I, right? And we can put star here. And then and this is whole prime, and then phi star prime, you can write, so this is for phi star, so e to the power minus I lambda phi star. Okay, and then for similarly for this part you will have a similar thing. So I will not write this because you will see that this is not needed in the end. So let's solve this part only. So del mu star prime will be just del mu star, right? So del mu doesn't transform under the gauge transformation, and here the IE a mu prime will transform like this, right? So you can write a mu star minus del mu lambda, or you can take the star outside the bracket. Okay, it's 2 bracket multiplied by this term, right? So and then you have the similar term here for the second d mu phi, and you see that I mean, if you multiply it with itself, you will see that there will be a residual term which will not cancel, right? So let's see that if it cancels out or not. So for the second one, you will have similarly del mu, so without the star, and here I e a mu minus del mu, and then here you will have I lambda psi, right? Now let's multiply these two together. uh, so you see, uh, here we have minus I e a to the power mu, and here we have plus, right? So these will cancel. uh, no, this will not cancel, because this will give you a mu term in the end, which will not cancel out by anything, right? Do you understand? So I'm saying, so here you have, for example, here you have this I e a mu term, and here you have plus I e a mu term, and these two will be multiplied, right? And in the end you will have a mu term, and this will not cancel out by anything. So you will not at the end get uh, this back. So that's why this will not be invariant under this transformation. So you will have other terms, but this term will be there. Okay, so you cannot have two del mu uh, together. Okay. Now let's check the this one. Okay. So I no no, we just saw here that when I was discussing, we saw that this term, when we introduce the d mu, this term becomes invariant under the gauge transformation, right? So, and this is the same term that is there in the Lagrangian. So we already know that this is invariant under the gauge transformation, like this. Okay. And now the remaining two, let's check for this one. So this is invariant because this is just from the Lagrangian. So psi bar psi phi prime. So this will be prime. Okay. Now psi bar prime is just minus I lambda psi prime. This is I lambda psi, and this is again I lambda psi. So what you get at the end is uh, this psi bar psi prime, because these two get multiply and give you 1, right? So you remain this one is remaining in the end term, and which is not equal to this. So this one is not invariant in the gauge transformation, right? And similarly the fourth option, which is a mu into a mu. So a mu transforms like a mu minus 1 by e del mu lambda, and this transforms like sorry, so when you multiply these two together you get a mu and you get other terms, right? Which does not cancel out. So this is also not invariant under the gauge transformation. So that's why these terms are not there in the Lagrangian, as we see here. Only these terms are allowed in the Lagrangian because they are uh, invariant under the gauge transformation. So you see this is the only term which is invariant in the gauge transformation, and which is the option 2 here. You understand? Yeah. Okay, so then we can go to the next problem. So here the same question is there. So given the above, so we saw in the last problem, which of the following cannot be a term in the Lagrangian? And these C1, C2, C3 are constants. Okay. So I just mentioned, so which cannot be a term in Lagrangian? The one who, which does not, which are not invariant under the gauge transformation, right? So what about this? What do you think? Can you guess? Mm-hmm. No, I'm asking why this cannot be in the Lagrangian. No, no, option one, option one. Can this be in the Lagrangian? You can just check. Why not? You can just check. No. Excuse me. What do you say? So when you take the gauge transformation on psi bar, you will get e to the power minus I lambda psi bar, and then e to the power I lambda psi. and this is seem to same as psi bar psi, right? So this can be inside the Lagrangian. Similarly, this also can be inside the Lagrangian, right? Now, what about these two? So, so we saw that d mu psi is invariant under the this kind of term, is invariant under the gauge transformation, right? It's but you have another psi here, right? And this will make this whole term not invariant under the gauge transformation. So we cannot have such a term inside the Lagrangian. Okay, so this option is this is the correct option, L3. So this cannot be inside the Lagrangian. And similarly here, here again, these two, this two will give you a invariant quantity, but then this phi will give you a invariant a term which is not invariant. Okay, so this is also not invariant in the gauge transformation, and so cannot be in a term in the Lagrangian. What is spinor field? Is this psi 1, psi 2, psi 3, psi 4? So this is the uh, field of this is the field of Dirac equation, which you use in the Dirac equation, right? This, oh, no, this phi is the scalar field, the complex scalar field, and psi is the spinor field. But both transforms like this. So here you see both under the gauge transformation, both are transforming like transforming similarly. Just here, this lambda is the function of x, and this lambda is a constant. Okay, it has a global gauge transformation, it has a local gauge transformation. Do you understand? So phi is just the two-dimensional complex scalar field. So yeah, this is the complex scalar field. So yeah, these two are the correct options. Okay. And then okay, let's go to the next question. So hypercharge of the tau quark. Uh, oh, sorry, top quark. So UT. We saw that this is the Gell-Mann-Nishijima formula, and top quark has charge 2 by 3, right? So you can just put, and the isospin of top quark is, so it is a part of the doublet I just mentioned. So this is the doublet for top quark and bottom quark. So it has isospin of plus half, right? So you can put here plus half, and then you can calculate hypercharge, which will be equal to 1 by 3. And if you calculate the, so you can just naively say that the hypercharge for bottom quark will also be uh, 1 by 3, right? Sorry. No, this is a simple problem. So any doubt here? Okay. Yeah, because the top quark and bottom quark, they form a doublet, so the hypercharge should be same for both. Now there is a statement that the left-handed and right-handed Dawn type quarks have the same hypercharge. So dl is equal to dr. Is it true? What do you think? Is it true or false? Yeah, tell me. So you're saying false, right? Okay, so let's see. So I just mentioned, so the left-handed quarks, they form doublets, right? Yeah. So the left-handed quark form doublet with the up quark, right? And I3 of dl is minus half. But the right-handed quarks, they are singlets. So their I3 is 0. Okay. So if you calculate the hypercharge using this formula, because the charge is same for both right-handed or left-handed, charge is same, right? So you will get hypercharge different for both. So that's why this is a false statement. They have different hypercharge always. Okay. Yeah. So okay, then there is another question. So which of the following have direct interaction with itself? So you have photon and W boson. So which one of them interact with itself? So does photon interact with itself, or does W boson interact with itself? So what happens? Do you have any idea? Yeah. No. No. So what is the difference between photon and W boson? Weak boson. Is there any difference? So, if you go through the lectures, you will see that W boson is a massive boson, okay? This has mass, while photon is massless. So that's why W boson can interact with itself via weak interaction. So you have, two W boson coming and one W boson going out. But this cannot happen with a photon. So you cannot have two gamma, two photon coming and one photon going out. Photon cannot merge or cannot split. But W boson can merge or split because they are massive. Okay, so this is not allowed, but this is allowed. Okay, so two photons cannot interact, but two weak bosons can interact. Okay, so let's we have another problem. Okay, so the left-handed and right-handed spinners are given as this, and we have to find which one of them is true. So let's first write the psi bar L, which will be psi bar, and this is 1 plus gamma 5 by 2. So why we can write this bar, I mean psi bar, why we can write like this? Because you see gamma 5 is given by like this, right? And if you so this Hermitian conjugate will be just minus I this, right, which is same as gamma 5. So that's why we get this for left-handed, and for right-handed similarly we will have 1 minus gamma 5 by 2. And then we can calculate these quantities to check which is the true statement. So the first one, let's put everything. 1 plus gamma 5 by 2 1 minus gamma 5 by 2 psi, and so if you multiply them, 4 1 minus gamma 5 plus gamma 5 and then minus gamma 5 whole square and then psi. So this cancels, and we know that gamma 5 square is just 1, right? I mean identity matrix. So this cancels with 1, so we get sorry, we get simply 0. So this is true, and then you can check for the second one. So psi L by R, psi R, here it's plus. So now you see that everything will be plus and this will not be 0. So this is not true, and this is a fact. So if you add these two, you will get psi back, right? So this is always true, and this I already derived here. So same is true for the, oh sorry, no, this is also not true. The psi L will be 1 plus gamma 5 by 2, right? Because you have minus 1 minus gamma 5, and if you take bar you will have 1 plus gamma 5. So this is what you get. Is it fine? Yeah, this is simple. Okay, so one last problem. So so given a scalar field like this, so this is a scalar field which is a doublet under SU2L, and phi 0 is electrically neutral. That means its charge is 0, and we have to calculate the hypercharge of phi. So how do you calculate the hypercharge of phi? So as I mentioned, the hypercharge of these both elements of the doublet will be same. So if you calculate the hypercharge of any one of them, it will be same for both. And since it's a doublet, so we can have isospin. So isospin of phi 0 will be plus half, and for phi minus it will be minus half. So you can put in this equation so Q is 0 plus half gamma by y by 2, and the hypercharge will be minus 1. Okay, same will be true for the phi minus, because it has Q equal to minus 1. So if you put minus 1 minus half for the I3 plus this, you will again get minus 1. So the hypercharge of phi is minus 1. Okay, any doubt here? Okay, thank you. So Yeah, this is the last problem. So let me know if you have any question to ask before I close the session. So I'll suggest to go through the lectures once if you have any thing, I mean, you have any doubt, and work out the problems yourself to gain confidence. Okay. Okay. So okay, then thank you for joining. I'm going to end the call. So bye.